I'm going to leave that here for 1 second. So Jacob, this is the first set of, yep, on the notes. First slide. Let me know when you're good and I'll move on. So you'll want to find that spot in your note packet. Trying to see if it would update pages, but it's not. There we go. So, large pieces of the lithosphere that move around the top of the asthenosphere. And probably at the end of class, I'll ask you what you've been taking and all that stuff before. All right, gonna move on. So why do they move? It is all back to the convection currents that we talked about last week or earlier this week even. That's that heat transfer from the core into the mantle, and it produces a very slow convection of that mantle material, because remember, that's not 100% solid. The mantle convection process produces lateral forces between the mantle and the crust, so it moves things side to side, and that'll probably make a lot more sense when we start looking at pictures. The mantle gets heated up by radioactive decay within our core and produces heat. So if you guys have ever heard of like nuclear power plants, anything like that, that is because that nuclear reaction goes through radioactive decay, creates heat, boils steam, and moves some turbines. Our inner Earth kind of does that same thing. So it pushes it around into different directions, leading to motion. Those plates move extremely slow, rates of only centimeters per year. So it's 2.5 centimeters in 1 inch. So in some places they don't even move an inch per year. Huh? That's been me all day. I'm so sorry. If you have your phone, Michael, take a picture of it. That way you don't have to go through the Nearpod again when it finally does respond. What is this? Is age theory, right? All right, moving on. All right, you have a quick 3-question quiz on your Nearpod. I can't hide your names apparently. Let's see. There we go. Sometimes my start bar won't go away. Go ahead and answer those 3 questions real quick. All right, I'm sure that last one's just kind of loading in. I'm going to reveal your name so you can see your score. All right. First question. Plate tectonics move very slowly. Slower than I could ever dream to talk. The Earth's crust is one solid plate. That is false. It's broken up into a whole bunch of different plates, kind of like we saw in that picture of the ice shield, or the ice floating on the ocean. Tectonic plates are large pieces of lithosphere. Again, you'll sometimes see that substituted with the word crust. Totally okay for this class. Oops. All right. So here's just kind of a picture of like a cross section of the Earth. You can see these nice pretty convection currents or convection cells and some of the features that they create. So we're about to talk about these different types of movements and boundaries and the features, the geologic features that come along with them. Are convection currents always these perfect, pretty little circles that we're going to work with? No, they're not. This is a little bit more realistic for you, where you can see red is really hot, and so you have this like really big plume coming up the center, a couple smaller ones. The cooler mantle sinking back down is not always a perfect circle, but we're going to pretend they are. So looking at this picture of convection currents, I'm going to put in one set of arrows at a time. If we have convection currents that are cooling off and then heating up and then cooling off again, going in this clockwise direction, is this little green plate above it, is it going to move to the left or, excuse me, to the right? Huh? Okay, we've got one to the left. This middle one, is it going to move to the left or to the right? We've got another left and we've got another right. In my, it'll make sense in a second. It is going to move to the right. All right, so it kind of takes that motion of that top arrow and goes in that direction. All right, so the next one, this one right here, it's going counterclockwise. Is it going to move this green plate to the left or to the right? We got a couple rights, couple lefts. It is going to move it to the left. So you have these convection currents actually moving kind of towards each other, and it's going to push these continents or these plates together and smash them. All right, one more. Now we have this side right here going counterclockwise. Is it going to move to the left or to the right? Which way is this top arrow going? It is going to go to the left. So you can see as the mantle, the currents come up, and then they kind of split apart. So it's going to go that opposite direction. All right, so you kind of, for me at least, it's looking at that top arrow and kind of following that direction in order for continents to either move together or move apart. Any questions on this picture? All right, you get to recreate it and draw it on your screen. Let's see how you do. You're recreating the picture that we just went through, so you're drawing in the convection currents. They don't have to be like perfectly pretty aligned arrows, but I need at least the general idea. Oops, sorry guys. All right, let's see what we got. All right, this one is exactly opposite. So this one, when we're moving continents together, we want it going clockwise and counterclockwise. When we're moving continents apart, we want this one going opposite ways. All right. Oh, as far as that one got is correct. Oh my gosh, so many arrows. All right, those are good, and those are good. Takes me a minute to look. Perfect. And Fabian slacking. All right, so earlier we talked about two different types of crust. We have continental and oceanic. Remember that continental crust is that thicker, fluffier, lighter crust. It is made of granite, which is a very light rock. It's also generally light in color, like white or gray. If you're in the Rocky Mountains in Colorado, you have pink granite called rose granite, just a little bit different. Oceanic is denser, more basaltic rocks, so your black or really dark gray rocks. Both of these are igneous that we're talking about, if you remember your rock cycle from middle school. Both types make up tectonic plates. So you have your continental crust, where it's land, your oceanic crust, which is at the bottom of the ocean. Both of these make up plates. All right. All right, so in your notes you have this table, the divergent, convergent, and transform. The divergent, these are the three types of boundaries that we'll be talking about, and there's like subcategories that we'll get into in a second. Hi. Oh. So there's three different boundaries that we'll talk about. The first one in this table is divergent. When you diverge, that means you move away. The effects it can have on our Earth is it builds new land. We'll talk a whole lot about seafloor spreading here in a bit. You see mid-ocean ridges, which is a fancy term for underwater mountain range, rift valleys, and seamounts. So seamounts being another fancy term for underwater mountains. Like there's a seamount building off the coast of Hawaii. Pretty soon, once it breaks ocean, then it'll be an island. Convergent, right there in the middle, that to converge means to move towards each other. Subduction is at most of these boundaries, and it recycles that crust back into the mantle. And then you have a term called orogeny, which means to build mountains. This creates oceanic trenches, which we'll talk a lot about today, mountains and seamounts. Both divergent and convergent boundaries have volcanic activity. Transform boundaries, this last one, has no volcanic activity. There's nothing really major that happens here other than earthquakes. It doesn't create new crust like divergent boundaries, and it doesn't destroy old crust like convergent. So it's just side-by-side movement. Everyone good? All right, we'll see how good you really are. 6 questions, 3 of them with pictures. All right, I'm going to reveal your name so you can see what you got. All right, and we are going to go over them. So first one, which type of crust is the most dense? That is oceanic, is the most dense out of these two. Don't confuse it with the most dense layer of the Earth. Okay, these are still pretty light compared to our mantle and our core and our inner core. All right, which of the following types of crust make up tectonic plates? It would be both continental and oceanic. Most of our granite rock is found in which type of crust? That is the continental. Oceanic is basalt based. It doesn't show me the pictures, but your first picture was a divergent boundary, then transform, then convergent. All right, so we're going to start talking about those a little bit more specifically, and all these differ. This is just a map of our general plates that we'll be talking about, and we'll be on a homework assignment. So when we talk about convergent boundaries, we have three different types of convergent boundaries. The first one down here is oceanic continental. So that's when you have an oceanic plate meet a continental plate, you get earthquakes, volcanoes, and ocean trenches. The next one up here is oceanic, where you get earthquakes, tsunamis, volcanoes, and island arcs, and we'll get pictures of those too. And then the last one in your notes is continental. That's earthquakes and mountain building, or the orogeny term. Hey. Sure. Really? Tell me when. Welcome back. Oh my God, Ashley, that's adorable. Oh, no, I hate my voice. Yeah, that's fine. All right, so our first type, and here's kind of a picture, is oceanic continental. My arrow got misplaced. Thank you, Nearpod. And you can see, if I can find my mouse, you can see where the oceanic plate subducts or goes through subduction underneath the continental plate. The one that the one that tends to subduct is the plate that is more dense. So the heavier the plate, the more likely it is to be the one to go underneath and get recycled back into the mantle. It creates those volcanoes. So this would be like the Cascades that go through California, Oregon, and Washington. Mount St. Helens blew up in 1980. All of that. That's kind of a local example. Another example is the Andes Mountains, like K2, all that area. And the rise in these mountains comes from the compression, from the convergence of the South American plate and the Nazca plate. It creates some of the deepest parts of our ocean, as well as the biggest earthquakes in the world. That's where the biggest ones have hit that we know of. Our second type, oceanic, is where two ocean plates come together. You get islands that start to form just like they did on the continent, except for it has to rise through the water first. Again, it's still going to be your densest plate, even though they're both relatively close. A good example is the Philippine Islands, and really all the islands in that area come from the Pacific plate and the Philippine plate converging together. We'll talk about this a lot here. The Mariana Trench, deepest parts of the ocean that we are aware of. You can even see it from space because it's so dark, so deep, and it actually outlines part of the Philippine plate, which if I had a map in front of you would make a little bit more sense. To give you an idea of how deep our ocean gets, especially in the Mariana Trench, this is about 7 miles deep underneath. It is a bigger distance than if you've ever been flying at a plane at 35,000 feet. It's cruising altitude, and you can't even pick out a house down below because you're so far up in the air. So it's deeper than that. It's deeper. You could fit Mount Everest inside. You could fit Pikes Peak inside. Any other, like Denver sits at about a mile high. You could fit 7 Denvers in there. And yeah, any kind of statue. So the Mariana Trench, like I said, it's 7 miles at its deepest point. They call it the Challenger Deep for that section of the trench, over 36,000 feet deep. The water pressure is 8 tons per square inch. So that is the equivalent of trying to balance and put 50 jumbo jets on your head. So you would be squished into non-existence and complete mush. This type of pressure is called hydrostatic pressure, and the temperature is about 33 degrees Fahrenheit at that depth. And it's warm because there's hydrothermal vents. Hold on, I forgot this slide cuts off. There's hydrothermal vents at the bottom. So kind of like you could think of hot springs, where it pushes up heated gases like methane and sulfur and warms the water enough for some deep sea creatures to live in. So just above freezing, like 1 degree Celsius. All right, hopefully everyone is keeping up. So here's some examples of what some of those deep sea creatures are. You have your hatchet fish, dragonfish. You can actually see in these pictures they have like eyes, but they don't work. There's no light that really makes it that far down to be able to see anything. So they've evolved from species that were able to see, but they can't. They also have some gnarly teeth too. Blobfish, which is totally one of my favorites because it's so ugly. Once, because it was under so much pressure at a very high or deep depth, by the time you pull any of these fish up to the surface, they're dead. That's why divers, if you've ever heard of divers getting like the bends, it's because they don't acclimate to different pressures slow enough. They do it too fast and it screws up your equilibrium in your body and can kill you. And it will with them too. You can also see he is lacking pigment. So because they can't see, there's no need to have fancy feather colors, anything super fancy down that deep. Goblin shark, looks like he can spear people with his head. Some smaller animals, you have a ping pong tree sponge. So obviously it looks like it's a lot of ping pong balls from a tree. And a sea nut, this is a type of jellyfish, and it actually still consists of the iridescence. So you have jellyfish that that can glow, or if you were in my classroom last year and saw my axolotl, he glows with UV light. So same kind of proteins in their DNA. Of course, Fabian. All right. Hopefully nobody in here is too freaked out by blood, right? All right. It's not that much. I have to. It doesn't work in my Nearpod, so I have to load it. Give me a second. You're gonna watch about a 2-3 minute clip of Mythbusters. So sad, Grant Imahara died. He's no longer with us. Gosh, you just keep finding more and more trash.
No, I'm just keeping.
The precursor to this is that the whole idea of Mythbusters is they hear a myth, they try and prove it correct or incorrect or busted. And this one was about a diver and what happens when the fail safes of your equipment don't work anymore. What's going to happen? So submarine, this is something like the Navy deals with the submarines, things like that. Any sort of deep sea divers have to worry about that equalized pressure. So that's kind of the background of this. Let me get, for those of you online, I'm putting the link in the chat in case it freezes for you.
Yeah. Ready in 3, 2, 1. I can't believe it! It worked! Oh my gosh!
Yep, the effect of the cut hose was less than instantaneous. But once the air pressure was exhausted, physics took over, and the drastic pressure differential pushed Meat Man into his helmet, exactly as the myth predicted.
I don't even think we need to bring him up. No!
Just leave him down there.
Wow!
Look at that.
That was
Look
gonna
at those
happen.
eyeglasses.
That's amazing. And you can't even see in the helmet anymore because it's covered with flesh and blood. Who's gonna clean the suit? Not it.
And a closer inspection of our diver reveals the kind of damage 135 pounds of pressure per square inch can do.
Oh, wow! Oh my God! We totally caved the helmet in! Look at all the guts in there. His stomach is inside his helmet.
Just by the side of the helmet. Look at that.
Dude,
Could you imagine that pressure?
that is absolutely confirmed. No doubt about it.
Totally confirmed. Okay, so I definitely expected the juices to be flowing, but I didn't expect to see them like slowly rise up through the helmet. And then blah, where everything just, it was like an explosion inside the suit. Completely unexpected, but totally awesome.
Now, the name of this game is differential pressure. They can withstand a huge amount of pressure when they're equalized. But the second you take away all the pressure on the inside, crush. You can see, this is what's left. I saw it with my own eyes. I still can't believe this actually happened. This one is completely confirmed.
I'm sorry, Meat Man, but it was totally worth it.
So that was only 130 pounds of pressure compared to the 8 tons of pressure that you would get at the bottom of the ocean. That'd be, if I remember my conversion correctly, it's like over 8,000 pounds. It's definitely way more than that. My conversion's off. Should be more. So that's hydrostatic pressure. That is also why your oceanic crust is more dense than your continental crust, because it's under all that pressure from the water. So make sure if you ever end up diving that you're safe about moving around. All right, back to the boring stuff. Continental convergence. You still get one of the plates subducting beneath the other one, creating more mountains, just typically not volcanic mountains. And it does take a lot longer for this crust to recycle back in, because it's got a lot further to go. An example is the Himalayan mountains, which are still growing by millimeters per year. They're formed by the collision of the Eurasian plate and the Indian plate. So they're still growing because India is crashing into Asia. All right. What are the 3 types of convergent boundaries? You can abbreviate if you'd like. 3 types of convergent boundaries. Emphasizing that word for a reason. All right, this is exactly why I do this question. So your correct answers are, looks like these ones right here, ocean and continent, continent and continent, ocean and ocean type plates. I always get people who submit this answer, and I want to make sure that you guys know the difference, that I asked about the 3 types of converging boundaries, not the 3 types of boundaries, which is why I was trying to emphasize that word. So that is exactly why I asked that question. All right, so we're going to talk about a couple different divergent boundaries now. We have seafloor spreading, which creates oceanic ridges or mountains, and then we have continental rift, which creates rift valleys. The only difference between these two is one is above water, one is below. There it is. So this is what seafloor spreading kind of looks like. You have your magma that comes up and creates new crust along this ridge line, and then it pushes, as it dries and solidifies, it pushes the previous seafloor away from it, moving the older stuff to the sides. Since I don't have any underwater picture examples, when looking at the seafloor, so everything in gray is a continent, so you have like North America, South America, Africa, Europe, Russia, all that stuff. Yeah. Okay. Thank you for asking. Right along this ridgeline right here is the one that we talk about typically the most when we talk about divergent boundaries. It's the Mid-Atlantic Ridge. So this is an underwater chain of mountains where new crust is always being created. And as you get further and further away, like towards the northwest side of Africa and the east coast of the United States where it looks purple, that is the oldest seafloor crust. So you have that down here as well, which is growing rapidly here in the Pacific Ocean, where the Nazca Plate is just off of South America. It gets real funky over here because you have a couple plates like the Philippine Plate that that kind of mix everything up a little bit. We're going to watch another short video. It's not as cool as the last one in my opinion, but it talks about the guy that really discovered all of this, and it really, as far as human timeline goes, was not that long ago. These questions are in your packet, so hopefully you can, they do go in order as well. So if you hear the answer to the second question, that means you missed the first one. So they do go right in order. I'll be asking you for the answers here soon.
World War II. German U-boats were on the prowl. To track them, the Allied forces developed new sonar methods, and scientists were enlisted to help survey the ocean floor. When the United States entered the war, Harry Hess was a geology professor at Princeton University. But he also happened to be a Navy reservist, so it wasn't long before he found himself in command of an attack transport ship in the Pacific. To help maneuver when coming in for a beach landing, Hess's ship was equipped with a depth sounder. Now, still being a geologist at heart, he used the sounder to measure the depth of the ocean floor whenever his ship was out to sea. Now, what he discovered startled him. Until the Second World War, most scientists imagined the bottom of the ocean looked like this. Flat, lined with nothing but sediment. But about 2 miles beneath the waves of the Pacific Ocean, Harry Hess discovered something else entirely. Mountains, like these here in California, with deep canyons and trenches, hundreds of high peaks that we now believe were once active volcanoes, and all of this at the bottom of the Pacific Ocean. Surprisingly, though, the discovery of the Pacific Mountain Range is not what makes Harry Hess part of our Great 100. Now, we'll get to that in a minute. To understand where all this is headed, I'd like to skip ahead to another event that set the geology world buzzing. For years, oceanographers surveying the Atlantic Ocean had taken sonar readings that indicated there was something down there, something big. In 1953, they found out what it was. a 12,000-mile-long mountain range. They called it the Mid-Atlantic Ridge. To fill us in, I paid a visit to Neil Driscoll, a geologist at the Scripps Institution of Oceanography.
One of the big discoveries that was made was that there was this ridge of underwater volcanoes that stood high above the seafloor.
How high is a mountain in the middle of the Atlantic?
The average seafloor depths are on the order of about 4,000 to 5,000 meters. The mid-ocean ridge sits up at about 2,500 meters. So they sit about 2.5 kilometers on average higher than the surrounding seafloor that's shown here in the deep blue colors.
So that's over a mile high.
Yes.
And that's where Harry Hess comes back into the story. Analyzing core samples and sonar readings from around the Mid-Atlantic Ridge, Hess made an astonishing discovery, a phenomenon almost beyond comprehension. The age of the Atlantic Ocean floor, he determined, was progressively older the further it moved away from the ridge. Harry Hess had discovered that the seafloor was spreading. He concluded that molten rock was being forced up from inside the Earth at the ridge, where it then formed into new crust on the ocean floor. Gradually, it was pushed away on either side as more molten rock continued pushing up from behind it. Hess called his great discovery seafloor spreading.
Harry Hess was in a position that he could bring it all together. Things were spreading apart and new Earth was being generated. But if you did this for long enough, the Earth should grow. And it doesn't.
The Earth doesn't get any bigger.
No. Harry appreciated the fact that if new Earth was being generated in one area, they have to be consumed or recycled in another area.
The process that recycles the crust of the spreading ocean floor back inside the Earth is called subduction. But as our next great discovery revealed, it's all part of a much larger process, perhaps the most powerful force on the face of the Earth.
All right, I'm gonna go back a slide. Okay. Oops. Wrong thing. All right. What was Harry Hess's background? Who caught that? Harry Hess's background. What did he do? Why was he out on the ocean to begin with? Do we need to watch the video again? No. Yeah. Yeah, he was a geologist. Very nice. He was also a Navy reservist, which is why he was on those submarines or ships, getting to get information about the ocean. Before World War II, what did scientists think the ocean floor looked like? Yeah, go ahead, Michael. It was flat, kind of like a desert, but underwater. Very good. What tool was used to discover the Mid-Atlantic Ridge? This one was probably the hardest one to catch. We still use it today. It's called sonar. It's the same way that whales get around. They use sonar. They don't have very good eyeballs. What happens to the age of the seafloor as it gets further from the Mid-Atlantic Ridge? Think back to the picture I showed too. What happens to the age of the seafloor? So we have our Mid-Atlantic Ridge right here. What happens to the age as it goes this way? Yeah. Yeah, it gets older, progressively older. What did Hess call his great discovery? See, yeah. That's all right. His great discovery is the seafloor spreading. Trust yourself. All right, and why doesn't the Earth get any bigger if the seafloor continues to grow and expand? You catch that one, Michael? Why doesn't the Earth get bigger if the seafloor continues to grow and expand? My online people, the video didn't work for them, so they're probably... All right, so that one comes back to subduction. Old crust gets recycled back into the mantle. So the Earth doesn't just like continually keep growing and expanding. If it did that, the inside of our Earth would be empty and we would implode on ourselves, which would be really bad. So we have that recycling of material because of subduction. So here's the above ground divergent boundary is a continental rift. A lot of times you get lakes forming in that area because it just creates a space for water to settle. A very common one that's referenced is Ethiopia. Ethiopia is getting torn apart because there's 3 plates pulling away from each other. And so sometimes you end up with these vast canyons. Fun fact, one of my favorite places ever, Iceland is the only place where the mid-ocean ridge breaks the surface plane of the ocean. It's the most volcanically active land on Earth, so I could drive around this island in less than a day, but there's still over 200 volcanoes and an average of 1 eruption every 5 years. In the next million years, Iceland will be about 25 kilometers wider. All right, what are our 2 types of divergent boundaries? like so far so good. Two types are continental rift zones and mid-ocean ridges. You guys paid attention to my wording this time. All right. The last boundary is a transform boundary. That's where two tectonic plates kind of grind past each other. The transform boundaries tend to have jagged edges that get caught on each other, and when it happens, massive pressure builds up and then it'll snap, and that creates an earthquake. This is the one boundary that has no volcanic activity. And just kind of a picture so you can see it. If you watch movies like, what was it, San Andreas with The Rock, it's all about the San Andreas Fault. That movie can't actually happen. It's very scientifically inaccurate, just for the record. But you can see the San Andreas Fault from above. This is what it looks like. You can see both sides of the plates. Once that snap and that pressure releases, a once straight road might turn into one that's curved. And you see this happen a lot with rivers too, that'll suddenly take a sharp turn. So we're going to take a pause here as far as notes go. We'll finish the rest up on Monday. I do want to point out a homework assignment. It's pretty quick, I think it's pretty easy. The boundary and stress types. It looks like this with a picture of all the different plates, and you have to identify, is it convergent, divergent, transform, and then you use this little key right here to tell you the boundary type. So I'll give you one quick example before the bell rings. The Nazca plate and the South American plate are right here. Their arrows are pointing towards each other. So that is a convergent boundary. Type, when we see them being pushed together, is called compression. Identify that for the map. And then we'll talk about the stresses is the last part of our notes, so we'll talk about that next time. If you guys don't have any questions or do have questions, ask them, or forever hold your peace. There's no DOL today. You'll get one when I see you again on Monday. Yeah, I'll see you again on Monday.